Not because there is a fire out there in any normal sense, but because when charged particles collide at those speeds, in that kind of near vacuum, the energy has nowhere else to go. It concentrates, it spikes. It creates something that looks, in the data, remarkably like a wall made of pure motion, standing guard at the edge of everything we call home. And then there was the magnetic surprise. For years, scientists assumed the sun's magnetic field and the wider galactic magnetic field were two separate systems, cleanly divided at the heliopause, like two countries with a fixed and simple border. Voyager 1's data suggested something far more tangled. The magnetic field lines from our solar system appeared to be connecting and interacting with the galaxy's magnetic field outside, exchanging energy in a process called magnetic reconnection. Our solar system, it turns out, is not magnetically sealed off from the galaxy. It is linked to it in ways nobody had properly modeled before this machine arrived to check. This is not a small footnote in an academic paper. If the boundary that protects our solar system is more connected, more dynamic, and more energetic than we assumed, then the models describing how that shield behaves over long stretches of time need to be re-examined from the ground up. There's something almost humbling in that. For most of human history, we assumed the edge of our world was a clean, simple line. Ancient sailors once believed the edge of the ocean was the edge of everything. Scientists a generation ago believed the edge of the heliosphere would be just as simple, a tidy border on a diagram. Voyager 1 showed us that the truth was messier, wilder, and far more interesting than the tidy version we had settled for. That pattern, it turns out, repeats itself throughout the history of science. Every time we actually go and look, instead of only calculating from a distance, the universe turns out to be stranger than our best guesses. So let's bring this into the present, because right now, in 2026, this story is entering what may be its final and most dramatic chapter. Earlier this year, engineers made a decision nobody wanted to make. In April 2026, NASA's Jet Propulsion Laboratory sent a command to shut off one of Voyager 1's remaining science instruments, a device that had been measuring low-energy charged particles almost continuously since the spacecraft launched in 1977. It was not broken. It was still working perfectly. It was switched off, simply because there was no longer enough power to keep it running alongside everything else the spacecraft needs to survive. Here is why. Voyager 1 gets its electricity from a container of decaying plutonium, slowly converting heat into power through what is called a radioisotope thermoelectric generator. At launch, that system produced close to 470 watts. Today, nearly 50 years later, it produces a small fraction of that, and it keeps losing about 4 watts every single year. Out of the 10 original instrument packages the spacecraft launched with, 7 have now been permanently switched off. In late February of this year, during a routine maneuver, Voyager 1's power dropped unexpectedly. Engineers realized that if the power fell any further, an automatic safety system on board could trigger, forcing shutdowns the team had no control over, and risking a recovery process every bit as dangerous as the one they survived back in 2023. So they made the hard call themselves before the spacecraft could be forced to make it for them. Notice how careful this decision-making process actually is. This is not a team reacting in panic. This is a team that sat down years in advance and mapped out, instrument by instrument, exactly which pieces of the spacecraft they would sacrifice, first, second, and last, based on which data mattered most. Even the small motor that rotates the recently shut down instrument was deliberately left running, using barely half a watt of power, purely so the door stays open for a possible restart later. Nothing about this mission has ever been left to chance. Every remaining watt of power is treated like it is precious, because at this point in the story, it is. But here's the part that almost nobody outside the mission team is talking about. They have not given up. Engineers are currently testing an ambitious plan, nicknamed internally as a total power restructuring, designed to reroute electricity across the spacecraft's remaining systems more efficiently, potentially freeing up enough power to keep instruments running longer, or even bring their recently silenced instrument back online someday. Because this plan is risky, they are testing it first on Voyager 1's twin, Voyager 2, which has slightly more spare power and sits somewhat closer to home, making any mistake less catastrophic. Those tests were scheduled for the middle of this year. If they succeed, the same approach will be carefully attempted on Voyager 1 itself. Nobody at NASA is promising success, but with this particular spacecraft, the history of assuming this story is finished has never once turned out to be true. Quick pause here. If you have made it this far, you clearly care about this kind of story more than the average viewer scrolling past it. So do me one small favor. Tap that like button right now, not because I asked nicely, but because it tells this platform to put this story in front of someone else who needs to hear it too. Consider it your own small signal sent out into the algorithm, hoping someone on the other end is listening. And now we arrive at a date that is no longer a rough estimate. It is locked into the calendar, confirmed by NASA's own calculations down to the second. On November 18th, 2026, at 16 minutes past 2 in the morning, Pacific time, Voyager 1 will cross a distance from Earth so vast that light itself will take a full 24 hours to travel between us and it. That distance works out to more than 16 billion miles, nearly 26 billion kilometers. A number so large, it stops feeling like a distance and starts feeling like an idea. Sit with that for a second. If Mission Control sends a message to Voyager 1 on a Monday morning, they will not know if it even arrived until Tuesday morning, and they will not hear a response until Wednesday morning. 2 full days just to complete a single exchange of words with a machine we built with our own hands. Right now, this year, this is happening for the first time in the history of our species. No civilization before ours has ever had a living conversation with anything this far away. Consider what Voyager 1 will have left behind by the time it reaches that mark. It will be more than 5.5 times farther from the Sun than the planet Neptune. It will have covered a distance that, if you tried to walk it at a brisk pace without ever stopping, would take you well over 300,000 years to complete. And it will have done all of this while never once refueling, never once receiving a repair from human hands, running the entire time on a power source that was already old technology when it was installed. No human-made object has ever reached that distance while still alive, still listening, still speaking back. And on that day in November, Voyager 1 will do exactly that, and then it will simply keep going. Every single hour, it travels tens of thousands of miles deeper into the dark. The delay keeps stretching, the power keeps shrinking, and sometime in the early 2030s, engineers expect the very last signal will arrive, be recorded, and then there will be nothing after it. But even in that silence, Voyager 1 does not stop moving. There is nothing out there to slow it down. No air, no friction, no gravity strong enough to meaningfully pull it off course. It will simply continue in a straight line, carrying something remarkable bolted to its frame. A gold-plated copper disc known as the Golden Record, holding greetings recorded in 55 human languages, the sound of rain falling through a forest, the sound of ocean waves, the sound of human laughter, alongside 90 minutes of music chosen from cultures spanning the entire history of our species. Carl Sagan, who helped design that record, once described it as a message in a bottle, cast into the vastness of the cosmic ocean. And that description has never felt more accurate than it does right now, long after every human city has crumbled, long after the sun itself changes and swallows the inner planets. That small golden disk may still be drifting through the galaxy, carrying proof that something curious once lived here, that we reached outward, not knowing if anyone would ever answer. Think about what the team who built that record actually chose to include, and what that choice says about us. They did not choose to send weapons diagrams or declarations of power. They chose rain. They chose laughter. They chose a mother's voice, a child's heartbeat, music built on instruments from every continent. Whoever eventually finds that record, whether that happens in 100 years or 100,000, will not learn that humanity was frightening or dangerous. They will learn that we noticed the sound of falling water and thought it was beautiful enough to send across the stars. Out of everything our species could have chosen to represent us, we chose tenderness. That decision alone says more about who we are than almost anything else we have ever built. By the time anyone or anything finds that record, if anyone ever does, human civilization as we know it may be almost unrecognizable, or may not exist in any form at all. And still, that golden disk will keep turning in the dark, carrying our laughter forward long after there is nobody left on Earth to laugh. Before we go into the final piece of the story, the part that even most scientists have not fully resolved yet, take 5 seconds and hit that subscribe button. Not for me. For the version of you that wants to keep learning things, most people never bother to look up. If this channel has earned 5 minutes of your attention today, it has earned 1 tap of your finger. Now let's return to that strange, steady hum Voyager 1 has been detecting in interstellar space since 2017, because there's a genuine open question at the center of it that scientists still have not fully answered. There are 2 competing explanations for what that persistent plasma signal actually is. One possibility is that it comes from natural thermally excited vibrations within the plasma itself. A real and interesting discovery, but one that mostly fits inside existing physical theory, without forcing anything to be rebuilt from scratch. The second possibility is something called quasi-thermal noise, a different physical process entirely, one that would carry information about the density and behavior of interstellar plasma in a way that could require real revisions to how we model this entire region of space. The difference between these 2 explanations might sound small if you're not a physicist, but it is not small at all. One explanation means interstellar space behaves roughly the way we expected, just with a few details filled in. The other means we have been missing an entire mechanism shaping the plasma between the stars, a mechanism that could change how scientists calculate the density, temperature, and structure of everything Voyager 1 has been flying through since 2012. It is the difference between confirming a theory and quietly discovering that a piece of the theory was incomplete all along. Right now, researchers cannot fully say which explanation is correct. Settling that question would require either more data from Voyager 1 itself, which is producing less every single year, as instruments are switched off one by one, or an entirely new mission built specifically to study interstellar space with modern instruments designed for exactly this purpose. No such mission currently exists. None is currently funded. And even if one were approved and launched today, it would take at least 25 years just to reach the boundary Voyager 1 already crossed back in 2012, which means that when this old spacecraft finally goes quiet, the question it raised may stay open for an entire generation. The only real-time window humanity has ever had into the space between stars will close, and it will not reopen for a very long time. That is the strange, uncomfortable truth sitting underneath this entire story. We are not simply waiting for Voyager 1 to eventually go silent someday in the abstract future. We are living through the final years of the only conversation our species has ever had with interstellar space. Whatever remains unanswered when that conversation ends will very likely still be unanswered by the time most of us reach old age. Here is what I think is worth carrying with you after this video ends. Right now, in 2026, the only living scientific instrument our species has ever placed in interstellar space is 49 years old. It runs on less electricity than the bulb inside your refrigerator. It was designed using engineering that predates the personal computer. And it is still sending home information that is genuinely reshaping how physicists understand the universe just outside our door. We have built newer machines, bigger machines that cost far more money and carry far more advanced technology. None of them have told us what this one has told us, because none of them have done the one thing that actually mattered. None of them have simply kept going, year after year, decade after decade, long past the point anyone expected them to stop. There is a kind of quiet lesson buried inside that fact, one that has nothing to do with astrophysics at all. Voyager 1 was never the fastest, the strongest, or the most advanced machine we ever built. It succeeded because it endured. It kept functioning through darkness, through failing components, through years when almost nobody outside a small team at JPL gave it a second thought. It did not need to be perfect. It only needed to keep sending its signal home, one faint transmission at a time, for nearly 50 years without stopping. Sometimes the things that end up mattering most in this universe are not the ones built to be spectacular. They are the ones built to simply keep going. There are some questions about our universe that can only be answered from inside it, not from a telescope pointed upward from a rooftop, not from a satellite circling our own planet. Only from something that actually crossed the line and kept transmitting back what it found. Right now, we have exactly one such machine. It is old. It is fragile. It is running on almost nothing. And every single signal it sends is a small miracle stretched across billions of miles of empty dark. Somewhere out there tonight, a 49-year-old machine built before most of us were born is still listening to the universe and still trying to tell us what it hears. It has survived cosmic radiation, corrupted memory, freezing cold, and a power supply that shrinks every single year without exception. It has done all of this quietly, without complaint, without ever once being asked whether it wanted the job. And it is still working. The only real question left is whether we are willing to keep listening back. If this story stayed with you the way it stayed with me while researching it, you already know what to do. Subscribe, tap the notification bell so you do not miss the next one, and leave a comment telling me which part of this made you stop scrolling and actually pay attention. Then, send this video to one person who still believes there is something bigger than us worth looking up for. This story deserves to travel just a little further than 4 watts of power could ever carry it alone. What if the loneliest machine ever built just sent home a message that no scientist can fully explain? Somewhere past the edge of everything we call home, a signal is crawling toward Earth right now, and it is carrying an answer nobody asked for. Before we go any further, hit like on this video, hit subscribe if you are new here, and share this with one person who still looks up at the night sky and wonders what is really out there. This story deserves an audience, not a scroll past. Let's start with a number that sounds like a joke until you understand what it actually means. 4 watts. That is roughly the power draw of a small nightlight. And right now, a spacecraft built in the 1970s is running on that much electricity, somewhere in a region of space so far away that sunlight itself is a memory rather than a presence. This spacecraft has no crew, no cameras looking forward, no modern processor. Its computer has less memory than a single text message on your phone. And yet, this tiny, ancient, half-forgotten machine is currently rewriting what physicists thought they understood about the space between stars. Its name is Voyager 1, and its story did not end when most people stopped paying attention to it. It kept going. It is still going. And what it has found out there, in the cold and the dark, far beyond anything human eyes have ever directly touched, is stranger than the plot of most science fiction films. Stay with me, because this is not just a story about a machine. It is a story about a boundary that protects every living thing on this planet, a boundary that may not be as stable as we believed. Most people assume that the age of great discovery in space happened decades ago, back when the Apollo missions were landing on the moon and the first photographs of distant planets were splashed across newspapers. It feels natural to think that everything worth finding has already been found, that the frontier has already been mapped, and all that is left now is refinement. But that assumption is wrong, and Voyager 1 is the proof. Right now, in this very year, an instrument older than most of the people watching this video is handing scientists data they do not fully know how to explain. The frontier never closed. We simply stopped looking at the one machine that was already standing on top of it. Let's rewind to where this all began, because the beginning makes the ending mean so much more. On September 5th, 1977, a rocket lifted off from Cape Canaveral in Florida. Strapped to the top of it was a spacecraft about the size of a small car, bristling with antennas and instruments built by engineers, using slide rules and hand calculations almost as often as computers. Its job was modest: fly past Jupiter, fly past Saturn, take some pictures, measure some magnetic fields, then quietly drift into irrelevance. NASA gave it 5 years, maybe less. Nobody expected a party for its 50th birthday because nobody expected it to see its 10th. But Voyager 1 did something almost no machine in history has ever done. It kept working. It flew past Jupiter in 1979 and returned the first truly close-up portraits of that giant planet's swirling storms. It swept past Saturn in 1980, capturing rings and moons in detail nobody had ever seen with their own eyes. And then, instead of shutting down like it was supposed to, it kept moving, kept measuring, kept whispering data back across the growing distance between itself and home. Along the way, it rewrote textbooks almost by accident. At Jupiter, it caught something nobody had planned for: a faint plume rising off the surface of the moon Io, evidence of an active volcano erupting in real time, the first time humans had ever witnessed volcanic activity happening anywhere beyond Earth. At Saturn, it revealed that the planet's rings were not simple, solid bands, but thousands of thin, braided strands, more intricate than anyone had imagined. Every flyby produced surprises the mission planners never budgeted for, because they had built their expectations on decades of guesswork from Earth-based telescopes, and guesswork, it turns out, only gets you so far. None of this was inevitable. Behind every discovery sat a small army of engineers, many of them young, many of them working on their very first job out of university, who spent years of their lives solving problems that had never existed before them. They wrote software for a computer with less processing power than a modern calculator. They built a spacecraft that had to survive radiation levels nobody could fully test for on Earth. And many of those same engineers, decades later, are still there. Older now, some of them nearing retirement, still showing up to keep this one machine alive. Because they understand, in a way most of us never will, exactly how rare what they built truly is. By the late 1980s, it had already become the most distant human-made object ever built. It kept that title and never gave it back. And in 2012, 35 years after launch, it crossed a line that no spacecraft had ever crossed before. It left the solar system entirely. To understand why that moment matters so much, you need to picture the sun not just as a source of light, but as the center of an invisible bubble. The sun constantly blows out a stream of charged particles called the solar wind, and that wind pushes outward in every direction, inflating a kind of cosmic shield around everything we know. Every planet, every moon, every asteroid, every human being who has ever lived. All of it sits inside this bubble called the heliosphere. At the outer edge of that bubble is a boundary called the heliopause. This is the point where the pressure of the solar wind finally runs out of strength, and the true ancient environment of interstellar space begins to press back. Everything on one side of that line is ours. Everything on the other side belongs to the galaxy itself. In August of 2012, Voyager 1 crossed that line. It stepped outside the only environment humanity has ever known and entered true interstellar space. Not a symbolic milestone, not a rounding error in a spreadsheet. An actual physical machine, built by human hands, now floating in the space between stars and still talking to us. And it kept talking. That is the detail that should stop you in your tracks. We do not just have historical data about interstellar space. We have a living, functioning instrument sitting inside it right now, sending back real numbers in real time from a place no telescope on Earth can ever truly see. For decades before Voyager 1 got there, physicists built careful models predicting what interstellar space should look like. These were not guesses scribbled on a napkin. They were built from decades of theory, tested and retested, published and defended, and almost all of them agreed on one thing. Interstellar space should be calm, thin, quiet, a kind of empty, drifting nothing between star systems, where particles barely interact and not much ever happens. Voyager 1 walked straight into that supposed quiet and found something else entirely. Starting around 2017, the plasma wave instrument on board began picking up something strange. A faint, steady hum, a kind of vibration running through the thin gas of interstellar plasma, appearing again and again, year after year. This was not a single strange blip that could be brushed off as a sensor glitch. It was consistent, persistent, detected across a stretch of space many times wider than the entire distance between Earth and the Sun. Researchers studying this data reached a conclusion that quietly unsettled a lot of very confident physicists. Interstellar space is not the smooth, sleepy void the models described. It has structure, it has motion, it has complexity happening at every scale, from distances you could measure with a ruler up to distances spanning millions of miles. In a very real sense, the space between stars is active. It has weather. What makes this even harder to dismiss is that Voyager 1 is not alone out there anymore. Its twin, Voyager 2, launched just weeks earlier, took a completely different path through the solar system, swinging past Uranus and Neptune before finally crossing its own heliopause boundary in 2018, 6 years after its sibling. When Voyager 2 crossed into interstellar space in a completely different direction and a completely different region, its instruments picked up strikingly similar signs of turbulence and structure. Two separate machines, launched decades ago, traveling in two separate directions, arriving at the same unsettling conclusion independently. That kind of agreement is exactly what makes scientists sit up and pay attention. This was not one faulty sensor telling a strange story. This was two. Think about what that actually means. Every single model of interstellar space ever built before this was built from the outside, from telescopes on Earth, from mathematics, from theory extrapolated across unimaginable distances. Nobody had ever had a working instrument physically sitting inside that environment, reporting back what it actually felt like from the inside. Now we do. And it is telling us we got something wrong. Here is where this stops being a story about faraway physics and becomes a story about you. That protective bubble, the heliosphere, is not just a scientific curiosity. It is a shield. It blocks a huge portion of the most dangerous radiation drifting through the galaxy. Radiation created by distant, exploding stars. Radiation that would otherwise reach much deeper into our solar system at far higher intensity. Every living cell on Earth exists in part because that shield holds. Scientists sometimes compare the heliosphere to the atmosphere that wraps around our own planet. We rarely think about the air above our heads, yet without it, nothing on the surface of this planet could survive the raw radiation of open space. The heliosphere works on a scale almost too large to picture, wrapping around the entire solar system the way our atmosphere wraps around Earth, quietly absorbing a portion of the violence happening across the galaxy, so that life here never has to face it directly. We have never had to think about this shield because, until Voyager 1, we had no way to actually measure how it behaves from the outside looking in. And what Voyager 1 is now telling us is that the environment pressing against the outside of that shield is more turbulent, more energetic, and more unpredictable than any model accounted for. Nobody is saying the sky is falling. But scientists who study this seriously are now asking a question they did not need to ask 5 years ago. If the pressure on the outside of our shield is behaving differently than we thought, what does that mean for the long-term strength of the shield itself? That question alone is worth sitting with for a moment, but the story does not stop there, because in 2023, this ancient little spacecraft nearly died. And the way it came back is one of the most quietly heroic engineering stories most people have never heard. For 5 straight months, Voyager 1 kept transmitting a signal. But the signal made no sense. It was garbled, corrupted, scrambled into something that even the most experienced engineers at NASA's Jet Propulsion Laboratory could not decode. The heartbeat was still there. The words had turned to static. Imagine dedicating your entire career to a single machine, listening to its voice for 30, even 40 years, and then one day, that voice simply stops making sense. Not silence, something worse. A sound you recognize but can no longer understand. That is what those 5 months felt like for the people who had given their working lives to this mission. Some of them had joined the Voyager team decades earlier as young engineers and were now nearing the end of their careers, quietly wondering if this was how the story would finally end, not with a clean goodbye, but with confusion nobody could translate. Eventually, the cause was found, and it was almost painfully small. A single memory chip inside the spacecraft's data system had degraded after nearly half a century of nonstop exposure to cosmic radiation. One tiny component, smaller than a postage stamp, had quietly broken down and corrupted the section of code responsible for formatting Voyager's scientific data before it was sent home. Now think about what it actually takes to fix that. You cannot fly out and replace the part. The spacecraft is more than 15 billion miles away. The only tool available is a radio signal, and even traveling at the speed of light, that signal takes over 22 hours just to reach the spacecraft. Another 22 hours for any reply to come back. Every single test, every attempted fix, required nearly 2 full days just to see if it had worked. Picture that process. You study the data, you form a theory. You write new commands. You send them out into the void, and then you wait. You wait almost a full day just to know if your instructions even arrived. You wait almost another full day to see what happened. And if you got it wrong, if a single command was flawed, there was a real chance you could silence the spacecraft forever, with no way to ever try again. Engineers at JPL worked through this for months, patiently, carefully, under a kind of pressure most people never experience in their entire careers. They eventually found a way to relocate the corrupted code into working memory elsewhere on the spacecraft, rewriting and testing each piece individually across those brutal 2-day communication cycles. It was, in every meaningful sense, long-distance surgery performed on a patient 49 years old, sitting further away than any doctor had ever operated before. There was no way to run a rehearsal, no identical backup spacecraft sitting in a lab on Earth where engineers could safely test their fix before sending it billions of miles into the dark. Every single command they wrote was, in effect, a first and final attempt, because a mistake could not simply be undone. It could only be followed by another 2 days of silence and uncertainty, wondering if this attempt had made things better or permanently worse. And they did this again and again, patch by patch, for months, never once losing the thread of what they were trying to save. In the middle of 2024, Voyager 1 came back online. Clear data, full sentences. And almost immediately, it resumed sending back more evidence of that strange, persistent plasma hum in interstellar space. The machine that should have died in 1981 had now survived its own near-death experience in the 21st century, and it came back with more secrets to tell us. If you are still with me, you already understand why this story matters more than most headlines admit. Before we go further into what happens next, drop a single word in the comments right now. Just type, listening. I want to see how many of us are actually paying attention to a machine that has been quietly changing science for years while most of the world looked the other way. Now let's talk about what Voyager 1 actually found at that boundary back in 2012, because this is the part where the story stops sounding like physics and starts sounding like something out of an old myth. For decades, the models predicted that crossing the heliopause should feel gradual, smooth, like a river slowly blending into the sea. The solar wind fading out gently on one side, interstellar space gently fading in on the other. That is not what the instruments recorded. At the heliopause, particles were not calmly thinning out. They were slamming into each other at tremendous speeds, generating temperatures that some researchers have compared to tens of thousands of degrees, right at the edge of our own solar system, in a region that was supposed to be cold and empty. Some scientists studying this boundary have described it, almost poetically, as a wall of high-energy particles. Try to picture that for a moment. A region of space far colder and far emptier than almost anywhere else humans have ever measured, somehow containing pockets of energy hot enough to rival the surface of a star.